So hello guys, I guess we can wait for like 5 minutes before so that a few others can also join the session. So it's 6:03 now. I guess we'll start at 6:10. So let's wait for 5-6 minutes for others. Okay, so I guess we can get started. So there are three people in the meeting. So hello everyone, I'm Lakshya Saggi. I'm the problem solving TA for the NPTEL Monday 6 to 8 p.m. sessions for the Games and Information course. So this will be our second session, and yeah, I believe like last week there was some confusion because of which like the session that's supposed to be on Mondays, but the announcement was made for Tuesdays last week, and there was some confusion. So I hope everything is cleared up. We'll be having these sessions on every week on Monday, 6 to 8 p.m. from now onwards. So this will be a second session, and in this session, we'll be discussing problems related to the Aumann model of computation, which was discussed in this week's lectures. So once again, since this is supposed to be a problem solving session, I'll be assuming that you guys have gone through the lectures and already know the basic concepts and theory. So yeah, we'll be focusing more on like problem solving. And in case of any technical issues, if you think if your video is not like if my screen is not visible or if my audio is not clear, or even like academic issues, if you are not able to understand anything at any point, feel free to stop me and like ask, inform me via chat. Like I'll try to answer, like in case of technical issues I'll try to fix them, and yeah, in case of any doubts I'll try to answer them to the best of my capabilities. So I guess we can get started then. I'll just share my screen and we can get started with solving the problems. So I'll just share my screen now. S- I hope my screen is visible to everyone. In case it's not visible, feel free to like please inform me via chat. Yeah. Maybe now we can get started. So yeah. So we'll be starting with some of the warm-up questions, I would say, because one or two of these questions have already been discussed in the lectures itself. So this will be more like testing whether you have seen strictures or not. Like not testing, but yeah, just sort of a revision for you guys. I'm not someone who's testing you by any means, but yeah. The first question is basically, yeah, maybe first let's just discuss the convention. It is a very commonly adopted convention that we'll be assuming that the Aumann model of incomplete information will be modeled using these three terms: the n, where n denotes the number of agent, the basically the set of agents; sigma denotes the sigma denotes the set of states, and fi denotes the uh, partition of the set of states for the agent type. So yeah, so if there are n agents, then we will have like n kinds of partition: f1, f2, f3 till fn. And now we can get started with the first question then. The first question says that yeah. First question says that let ki be the knowledge operator for the player I, and a comma b belongs to like omega. Omega is also sometimes adopted as a set of states. Maybe it's better I should just write it as sigma, because just to have the same convention everywhere. Yeah, this just means that uh, we have ki is the knowledge operator for the player I, and if there are two sets of states A and B, uh, we can think of this a set of states as like what we call an event, right? This was described as an event in the lectures. Given two events A and B, then ki of A intersection ki of B is equals to ki of A intersection B. Is this statement true or false? Would anyone like to answer this in chat? Okay, so Satvik is saying that this is true. So yeah, good job, Satvik. So actually, this is true, and like this was discussed in the lectures also. Uh, you can actually mathematically prove this also. You can just use that the partitioning for the set A intersection the partitioning for the set B, and like you can assume an arbitrary partitioning of the set for this for the player I, Like you can assume an arbitrary function fi for the player I, and you can show that this kind of thing will hold using sets. But a high level intuition of why this should hold is like what was also described in the lectures that like maybe I should just describe the intuition here. The intuition is so what does Ki of A represent and Ki of B represent in this Aumann model? Ki of B represents the knowledge, like where the knowledge whether event B has occurred. For the player I, uh, does the player I know that the event B has occurred? Similarly, Ki of A denotes something like the knowledge for player I if event A has occurred. And now, what this statement is essentially claiming is if the agent I knows that event A has occurred and I knows that event B has occurred, then essentially this means that A and B both have occurred. Like A intersection B means that A and B both have occurred. And so now if independently I knows that A has occurred and I knows that B has occurred, then I also knows that A and B both have occurred, right? So that's why both these things are equal. If someone tells you that events A and B both have occurred, then you can say that event A has occurred independently and event B has also occurred independently. And also, if event A has occurred independently and B has occurred independently, then A and B both have occurred independent, like both have occurred together. So yeah, maybe I should like do away with the intuition here. Yeah, because this same argument has been discussed in the lectures also. So yeah, good job, Satvik. The correct answer is true for this one. And then we come to the second question. Second question says that I will again be adopting like Ki be the knowledge operator for the player I again, and A is let A be an event. Then Ki of A, whole complement of this. So the whole complement of Ki of A is equal to Ki of A complement. So is this statement true or false? Does the question first of all make sense to everyone? That this basically denotes that we first take the event A, then we take this Ki operator over A. So we have this set now Ki of A as a set, and we take the whole complement of this. Then we take the complement of this whole set. Whereas the second term here denotes we first take the set A, then we take its complement, and then we take the knowledge operator over the whole set. Like maybe it should be written like this so that it's a bit clear to everyone. Yeah. First we take A, we take the complement of A, then we take the knowledge operator over that, and then we again take the knowledge operator over that. So is this statement true or false? Okay. So Satvik is saying that this statement is true, whereas Priyanshu is saying this statement is false. Would you guys like to think out it for a minute more? Like because one of you is definitely like the answer can't be true as well as false, right? So just take a minute, guys, and think about it if any of you wants to change your answer to this. Essentially, on an intuitive level, maybe here we can show something more mathematically, but I'll try to like in this first question I gave just an intuition, but in second question, since this was directly discussed in the lectures, in this I would like to give a uh, like this is something different from what was discussed in the lectures. In lectures also one something like this was discussed, but not exactly this. And so for this, I would like to present a mathematical argument in the explanation. But what this is essentially saying on a high level is if I knows that an event has not occurred, an event A has not occurred. If I has knowledge of, if I has the knowledge that event A has not occurred, then that is equivalent to saying that I does not have knowledge of A occurring. Okay. Uh, Satvik is saying self-aware in Aumann's model, self-awareness follows. Yes, Satvik, self-awareness follows. So actually, I think the answer for this is not true, but rather false. Maybe I'll try to explain this also. So Priyanshu changed his answer from false to true, but actually it is false. So yeah, correct, Satvik, that self-awareness follows in Aumann's model. What this means is maybe I'll just type out, since self-awareness is free in Aumann's model. This means that this term ki of a complement is essentially equal to just, you can like remove first ki. That I has the knowledge that I has the knowledge is equivalent to just saying that I has the knowledge. So essentially the question boils down to, so the boils down to whether something like this holds, right? Like I can remove the first ki, so I have to tell whether ki of A's whole complement is equal to ki of A complement. Oh, so yeah, Satvik, you got it. That's nice. And yeah, so these two things. Uh, so one thing is saying that the agent I has knowledge of the agent I ki of A denotes that agent I has knowledge of the event A, and its whole complement means that agent I does not have the knowledge of event A, whereas the right side claims that agent I has knowledge of A not occurring. So here I does not have knowledge of A occurring, whereas here I has knowledge of A not occurring. Also, like this was also discussed in the lectures only, that this kind of thing does not hold, right? This was discussed in the lectures itself, that there is no relation between ki of A's whole complement and ki of A complement. Like there is no equality relation. Like you can easily construct examples for this where these two things are not equivalent. But I think uh, you can do it as an exercise or try it yourself. So yeah, yeah. As discussed in the lectures, this statement is false. Yeah. And yeah, maybe just this is false. And maybe just a homework exercise for you guys, just to understand the concepts better. So what you try to yourself, construct an example where or maybe just construct an Aumann model, maybe where this is not equal to this. So we know that like this statement is not true, right? This is false. So there must be some examples of Aumann models where this is false. And it's not too hard to construct such an example where these two statements are not equal. But just as a homework, maybe you can try this. First of all, like, okay, again, like, I'm just reiterating that if any of you has doubts at any point, then you should like ask in chat. And if you don't ask, I'll just have to assume that everything is clear. Okay. So second is false, first is true. And yeah, maybe we can have an additional question here, like which we can discuss. So, um, so maybe like a note. So here we discuss this with respect to the intersection, right? We discussed that ki of A intersection ki of B is equal to ki of A intersection B. And this was discussed in the lectures that this kind of thing is true. But what happens if uh like if intersection we replace it by union? Maybe I'll just write it as a union like this. Since or maybe I'll just maybe just copy the union operator. Just copying the symbol from here. Is this true? False. So any guesses, guys? For this kind of problem, like if like for intersection, we know that this was discussed in the lectures also that this intersection this is equal to this. But here like ki of A union ki of B is equal to ki of A union B. Is this statement true or false? Think about it for like 2-3 minutes. I think this is an interesting question because this has not been discussed in the lectures also. Like any answers or any guesses even from anyone? Like, what does this mean? This means that uh, I has the knowledge of event A. This means that I has knowledge of event B, and this is like something like I has knowledge of event A union B. Okay. So Satvik is saying that the answer here should be uh, true. Any guesses, guys? Anyone else? Like, do you guys think that is this true or is this false? Okay, so actually, Satvika, I think the answer for this will be false. Like, yeah, the first intuition may be that, okay, this might hold because, like, if one thinks intuitively that A occurs or B occurs, then at least one of A or B will be occurring or something like that. But actually, we can have, like, uh, like here also we just discussed it intuitively, but note that intuition is not something by which we should be proving things. Like, we should actually be showing things via mathematics, right? These all operators are defined well defined mathematically, and like we can have a Aumann model where like this kind of thing does not hold. And I can give an example for this also. So suppose suppose maybe we can have the set of states. Maybe we can have the set of states. Sigma is equals to just 1, 2, 3, 4. So we have, let's say, just 4 states and f of I. F of I is the partition with respect to I. The partition is something like maybe 1, 2, and I guess 3, 4. Okay. And Let the event A is equals to 2 comma 3 and B is equals to 1 comma 4. So if this is the thing, like let's say, I hope everyone understands the convention that this is like this sigma is like the set of states, then fi is the partition for the player I with respect to the set of states. And now we have these sets A and B which were asked in the question. A is 2 comma 3, B is 1 comma 4. Now maybe we can look at these two things, what happens to these two things. So what will be the first of all guys so here what will be the value of ki of A? What will this set look like? The knowledge operator when applied to A. Anyone? For this kind of setup, what will be the value of ki of A? So with respect to like any partition, like we know what the knowledge operator says, right? What this is essentially saying, like event 2 or 3 has occurred, can I have knowledge of something like this? But note that 2 and 1 are actually indistinguishable. And similarly, 3 and 4 are indistinguishable for the agent I. So what this means is like neither 2 nor 3 can be part of like the knowledge of I. So yeah, actually, like this is what Satvik has written in chat also that this will be phi. I'll denote the empty set as like this phi. And similarly, it can be seen that K of A is phi and what will be the value of Ki of B? Again, like here we said that A consisted of 2 comma 3, but note that no subset of this set, like no subset of 2 comma 3 is like in the same kind of set in the partition, like 2 and 1 needed to be together if we wanted to include 2. 2 and 1 need to be part of A if we wanted to include 2. Similarly, 3 and 4 needed to be together if we wanted to include 3 in the Ki of A. Similarly, if B is 1 comma 4, then what happens? Then what happens is again like we have a similar thing like 1 cannot be part of Ki of B because uh, 1 and 2 are indistinguishable and B does not contain the element 2. Similarly, 4 also cannot be part of Ki of B because 3 and 4 are indistinguishable, but 3 is not the part of B. This is also like straightforward from the lectures. So Ki of A and Ki of B both are phi. And what this gives us is this implies that what will be the value of Ki of A union Ki of B? So there are two empty sets. So their union will also be empty, right? Because union of empty sets is an empty set. Okay. And but what will be the value of A union B? A union B will be equal to like we know that A union B will be equal to like a union of 1, 2, 3, 4. So it will be like something like 1, comma 2, comma 3, comma 4. And now if we take the knowledge operator over this, Ki of this set 1, 2, 3, 4, then what will we get? For this, I expect answer from you guys uh, like If you have gone through the lecture, I think you should be able to answer it. This thing, like what will be the value of ki of A union B here? Yes, exactly, Satvik. So ki of A union B will be equal to 1, 2, 3, 4. So good job, Satvik. So yeah, so this implies. And why is this the case? Because again, as we defined in the definition, like let's see from 1 to 3 4 what elements can we include. So if we wanted to include something like a 1, then 1 and 2 need to be together, and 1 and 2 are indeed part of A union B. So that's why 1 and 2 both can be part of the Ki of A union B. Similarly, we see the 3 and 4 needed to be together. And we see that actually 3 and 4 are indeed together in A union B. So they will be present in Ki of A union B. So here we have an example where Ki of A union Ki of B was empty set, but Ki of A union B was uh, basically the whole set of states, sigma. So this shows that Ki of A union Ki of B is actually not equal to Ki of A union B. Hence, the claim is false. So I hope everyone understood this. If not, please feel free to ask in chat. I'll try to answer this. So note that uh, like one might think directly based on intuition again. Again, what I'm saying is intuition is something which you should not go by. Mathematics is what you should go by, because all these things are defined by maths. So one might intuitively think like the intuition which we gave here. Here also we need some, actually we need to show a mathematical proof that this statement is true. And maybe you can try this yourself, as this has been discussed in the lectures also. Uh, so here, like one might intuitively think, okay, what does, if I has the knowledge of A occurring, or I has the knowledge of B occurring, then I has the knowledge of A or B occurring. But if I has, and similarly, like if I has the knowledge of A or B occurring, then I has the knowledge of A occurring or the knowledge of B occurring. One might think that this holds via intuition, but actually, like mathematically, you can see that this claim is false. Okay, so maybe you guys can take a look at it for a minute before we move on to the next question, because I think this kind of example is interesting and maybe shows like why the knowledge operator is important and why is it non-trivial. Maybe just take a look at this example for a minute before we proceed on to the next problem. I think maybe we can move to the third question now. Yeah. So third and fourth question are based on the probabilistic model, which was discussed at the in the last lecture for the week. So this is the common data for the question 3 and 4. So consider an Aumann model of incomplete information with beliefs in which we are given that the n is basically the number of agents. So there are two agents, 1 and 2, and the set of states is basically 9. And the partitioning with respect to agent 1 and agent 2 is given to us. So it's to agent 1, it is 1, 2, 3, 4, 5, 6, 7, 8, 9. With respect to agent 2, it is 1, 2, 3, 4, 5, 6, 7, 8, and a 9. And probability of occurrence of any state is equals to 1 by 9. Then the question asks us that If the event A we define by 1, comma 5, comma 9, then and the true state of the world is basically 9, then we need to calculate the first question answers the first order belief of player for omega equals to 7. Like what's the first order belief for player 1 for like omega equals to 7 state. Note the true state of the world is given to us as 9, and what will be basically the posterior belief for player 1 for the state omega equals to 7. So basically, the prior is given to us as 1 by 9 for all the states that all agents believe that all states occur with equal probability of 1 by 9. But now, like, if the true state of the world is 9, then how will the belief for player 1 change for the state omega equals 7? So Darshan is typing. Darshan, you have typed something. Uh, what do you mean here, Darshan? 2 1 x answer. Sorry, I don't understand what you have written in the chat. Uh, so can you type it again? What have you written? Like, I think it has some typos because of which I'm not able to understand what you have written. And in the meantime, like, if Darshan, while Darshan is typing, maybe would anyone like to answer this third question? Like, if the true state of the world is 9, then how will the first order belief for player 1 change for omega equals 7? Oh, Darshan is saying to explain the second question. So Darshan, actually we discussed the second question already. I think you joined the session a bit late, maybe. So you can view the recording actually, and the second question has already been discussed. Like it's not too difficult, by the way. Like we just the question just asked whether this kind of thing holds true or not, and we showed that this kind of thing does not hold true. And this was like mostly from what was discussed in the lectures. This was not too difficult to see. Maybe you can view the recording afterwards and you will be able to see why is this. Till then, maybe we can move on to the third question. So Satvik is saying for the third question, the answer is 0. Uh, why do you think it would be 0, Satvik? See, what do these kinds of question entail? So maybe we can first uh, see. This was already discussed. This was discussed in the lectures, but I'll try to explain it from a different perspective so that maybe if two different kinds of explanations are available to you, maybe you can understand or grasp it a bit better. So what does this question actually mean? In the Aumann model of incomplete information, what do we know? These partitionings essentially mean that the player can't distinguish between these states. So if a state 1 occurs in the real world, the player 1 does not know whether the state is actually 1, 2, or 3. Player does If 1 occurs in the real world, the player definitely knows that I'm talking about this f1 only, the player 1 only. Then the player definitely knows that 4 5 6 and 7 8 9 have not occurred, but player can't distinguish between 1 2 and 3. Okay. And similarly, like if the state 5 has occurred, then this player knows that one of the states of 4 5 and 6 have occurred, but definitely 1 2 3 and 7 8 9 have definitely not occurred. And if the player already has some prior belief that all the states should have occurred with equal probability. Suppose I'm someone who has a prior belief that any everything, like all of these states are basically like what is actually happening in the world. So what actually happens in the world, everything has equal probability of happening. Then what happens is if I see that suppose in the real world actually the state 5 happens, but I don't know actually 5 has happened. I just I can just observe that like I cannot distinguish between 4 5 and 6. I can just say that one of 4 5 or 6 has happened. I can definitely rule out 1, 2, 3, and I can definitely rule out 7, 8, 9. But I can't distinguish whether 4, 5, or 6 have occurred. And I had prior belief that all states are occurring with equal probability because here we are given, let's say. So now how will my belief change? I know that all these states are not occurring, but the remaining states, my belief will still be that the remaining states may be occurring with equal probability. It's kind of like that. And maybe if all the states were not occurring with, like, if the probabilities were not equal but rather something different, then we could say that these states would be occurring in the probabilities which are proportionate to like what were our prior beliefs. So I hope you guys understand the high level idea. Like I don't know actually what state is occurring. I can only rule out some of the states, and between the states remaining, I have to invoke my prior beliefs to see what will be the probabilities. So now Satvik has written in chat that is the answer 1 by 3. So yeah, Satvik, actually good job. So actually the answer is 1 by 3 for this. So maybe we can discuss this here. Okay. So we are talking about player 1, and we are talking about omega equals to 7. So note that the true state of the world is equals to 9. What this means is that the player 1 definitely knows that it is not anything from 1, 2, 3, or 4, 5, 6. That player 1 knows that the state is one of these 7, 8, or 9. The player cannot distinguish between these three, but knows that it is one of these three. Right? One second, guys. Sorry for that. So, yeah. So it knows that one of these three is occurring, like one of the 7, 8, 9 will be occurring. And we know that all of these were occurring initially with equal probabilities of 1 by 9. So now we know that one of the 7, 8, 9 states is occurring. So other states have probability of occurring as 0. But in these three states, initially, since they occurred with equal probabilities, afterwards also they will occur with equal probabilities. So what we mean is one of these three states is occur. Like the player 1 will think that one of these three states is possible, one of 7, 8, 9 is possible, and all these will have equal probability of 1 by 3, 1 by 3, 1 by 3. So what does this mean? That what player 1 will think uh, is actually that the state 1 occurs with a yeah the state 1 occurs with 0 probability, 2 occurs with 0, 3 occurs with 0, 4 occurs with 0, 5 occurs with 0, 6 occurs with 0, but 7 occurs with 1 by 3, 8 occurs with 1 by 3, and 9 occurs with 1 by 3. So this is what will be the first order belief for player 1 for all states. So similar for omega equals to 7, for the state 7, it will be actually 1 by 3. For 6, it would be 0, 5 would be 0, 4 would be 0, and so on. But for 7, it would be 1 by 3. So answer here would actually be 1 by 3. Maybe I should write this down so that it's easier for everyone to follow. So since the true state of the world is equals to 9, but layer 1 cannot distinguish between the states 7, 8, 9. So what's the probability? Maybe I should write probability as PR. So probability that probability of player 1 for something like omega equals to 7, given that omega star, the real world, is 9, will be nothing but uh, uh, how you applied like something like a Bayes rule earlier. Or maybe like, should we be writing like this? I think this takes away a lot of intuition from the calculations. So I don't like writing like this because it takes a bit away from the intuition. Hmm, how should we write this so that everyone is still on the same page? Hmm. Okay, maybe we should not write it like this. Uh, we can write it something like this. So yeah, since the true state of the world is 9, but player 1 cannot distinguish between the states 7, 8, 9. So mm, player 1 assigns probabilities posterior probabilities to the states 7, 8, 9. Note that uh, in lectures, they directly discuss using equations, but these equations essentially boil down to these kinds of argument only. Like you can write it in something like using Bayes rule, like probability of A given B as probability of A intersection B given probability of B and stuff like that. But I'm not writing it like that because I want to give you guys a bit more intuition. Like you can use the same formulas which were discussed in the lectures and you will arrive at the same things. But I'm just trying to give a bit more intuitive argumentation for things. So player 1 assigns posterior probabilities to the state 7, 8, 9 in proportion to their prior probabilities and assigns all other states probability of 0. So player 1 knows that like 1, 2, 3, and 4, 5, 6 have probabilities of 0 because these states cannot occur since we player 1 can already distinguish between like 9 and all of these states. But between these three states, the player cannot distinguish between 7, 8, 9. And so if I initially believe that out of 7, 8, 9, like 9 has a higher probability, like in this prior belief, if 9 had a higher probability of occurring, then I would have thought in the posterior belief also that 9 has a higher probability of occurring. So that's why what we are doing is what we want is one of these states will be occurring, one of these 7, 8, 9 states will be occurring, and uh, one of these states will occur. So the sum of their probabilities of occurrence should be equal to 1. And also their probability should be in proportion to their prior probabilities. Like whatever the prior probabilities were, in the same ratio, the posterior probabilities for these three states should be. And this is something which we'll be saying. So since the prior probabilities for 7, 8, 9 are equal, hence the posterior probabilities will also be equal. And what does this mean? So let's assume let this probability equal to x. And now, like if we have this probability equal to x, or maybe let's just say p, small p, then we know that the sum of probabilities over all possible states should be equal to 1 because we are we are assigning probability such that their sum is equal to 1. So suppose we assign a probability of p to the state 7, p to the state 8, p to the state 9, and 0 to all other states. Then since the probabilities should sum up to 1, we get that p plus p plus p, because 7, 8, 9, all of these have been assigned probability of p because their prior probabilities were equal. So p plus p plus p should be equal to 1. And this implies that we get that p equals to 1 by 3. So this is our answer that the first order belief of player 1 for omega equals to like 7 as well as 8 as well as 9 is equals to 1 by 3. Note that like even though true state is 9, the player 1, since he cannot distinguish between 7, 8, 9, he cannot like directly say that the true state is 9. He'll have to like maintain a probability distribution over the states he cannot distinguish. So hence the answer for this is equals to 1 by 3. I hope this is clear to everyone. If it is not, like, please ask me in chat, because this is somewhat the most numerical part of the whole like assignment, and I think a similar question is asked in this week's quiz also. But it's not too difficult once you grasp the high level idea, like what does prior mean and what does posterior mean, right? So the answer for this question is 1 by 3, and like which is something like up to 2 decimal places you can write it as 0.33 or something like that. Now let's move on to the fourth question. So fourth question says that again, if the true state of the world is equals to 9. So again, we have that true state of the world is equals to 9. Calculate the probability that player 1, again we are talking about player 1, ascribes to the event A. And we are given the event A equals to 159. So what is the probability that player 1 ascribes to the event A, where A is the event 159? And what does ascribes mean on a high level? This means that what's the probability that player 1 thinks that event A has occurred? Like, since the player is maintaining a probability distribution, he cannot say for sure, but what's the probability with which player 1 can say that the event A has occurred, where A contains the states 1, 5, and 9? Okay, so Satvik is saying 0.33 again, whereas Priyanshu is saying 1 by 2. So Priyanshu, why do you think it should be 1 by 2 here? Uh, like I'm just curious, like this from where do we get 1 by 2 here? Okay, Priyanshu is typing something in the chat. So yeah, so Priyanshu is writing that conditional probability is given by 1 by 9 divided by 1 by 3. So yeah, so actually it is so what you have written, this fraction is equal to 1 by 3, not 1 by 2, na? Yes, so Satvik exactly so both Priyanshu's and Satvik's. So Darshan has also written the answer. So all of you have arrived at the correct answer. I think it was just a typo by Priyanshu who wrote 1 by 2 initially. So Priyanshu's conditional probability is formula is correct. So yeah. So good job, guys. Like answer is 1 by 3 and yeah, like Priyanshu described, you can find out the conditional probability from the formulas given in the lectures. It's not too hard. Just probability of A given B is probability of A intersection B divided by probability of B. But to just get a more intuitive idea of what's happening here, like why I like to give a more intuitive idea because it's still I would like to still give a mathematical idea, but from a different perspective, like a mathematical argument from a different perspective, because this can help us think of the same things in multiple ways, and which can enhance our the reasoning, in my opinion. So my way of thinking is similar to Satvik that the event A about which we are going to describe, what event A says is either 1 has occurred, or 5 has occurred, or 9 has occurred. What's the probability that one of these three has occurred? 1, 5, and 9, right? When the true state of the world is given as omega star is 9. Like, what's the probability that player 1 thinks that one of these three things has occurred, 1, 5, 9, when the true state is 9? So we know that when the true state is 9, the posterior probabilities that the player 1 has assigned is basically it has assigned a probability of 1 by 3 to each of these 7, 8, 9, and 0 to everything else. And so what this means is in for player 1 knows that the event 1 occurs with 0 probability, the event basically the state 5 occurs with 0 probability, and the state 9 occurs with actually 1 by 3 probability. So these two states have 0 probabilities and this has 1 by 3 probability. So maybe you can sum up the probabilities and say that uh, basically the event A occurs with 1 by 3 probability. 1 by 3. And like, yeah, maybe since layer 1 assigns posterior probabilities of 0 to 1 comma 5 and 1 by 3 to 9. Yeah. So basically the event A, which is 159, will be just some of these, which will be 0 plus 0 plus 1 by 3, which is 1 by 3. So I hope everything is clear. The same thing you will get. So I'm not doing anything different or anything new. Don't think of this as uh, a different derivation or anything of what you must have seen in class. It's just the same thing, but seen from a different perspective. So it's not this is something which is a completely new concept or anything. I'm just trying to simplify the calculations. So I hope this is clear to everyone. Similarly, suppose if it was not 159, but rather something let's say 789. Let's say the event A was instead of 159, it was 789. Then what would be the probability that player 1 ascribes to that event? If the event was instead of 159, it was 789. I'm not writing this because, yeah, exactly, Satvik. So good job. So if the event was, let's say, 789, then the probability would have been 1. Because, like, uh, player 1 knows that 1 of 789 is true. So event A occurs with a probability One can think that 7 occurs with 1 by 3 probability, 8 occurs with 1 by 3, 9 occurs with 1 by 3. So their sum is actually 1. So good job, Satvik. So it would be 1 in that case. So I hope this is clear to everyone. Then maybe we can move on to the next question. Okay, I think, yeah. Again, I have written omega here. I'll just copy the sigma operator. 1 second, guys. Yeah. So let's move on to the fifth question now. Fifth question says that Anthony, Betty, and Carol are each wearing a hat. So let's think of these as Anthony's A, Betty's B, Carol is C. So A, B, C are each wearing a hat. Hats are of like red or blue color. Hat can be, there is like the hat which they are wearing, like one of those can be wearing a red color hat or a blue colored hat, similarly for the other, similar for the other. And each of the three sees the hats worn by the other two, but cannot see their own hat and therefore does not know its color. So A can see B and C's hat's color, and C can see A and B's hat's color, and so on. Now we have to model this as an Aumann model of incomplete information. And yeah, one can think of multiple models, but there will be a very simple model by which you can model all of this, right? And the notation we'll be using is you like to use is uh, omega ijk represent the state of the world where Anthony has I color hat, Betty has J color hat, and Carol has K color hat. So note that like I, J, and K will take the values of something like R or B's. So first of all, we need to model the world in this kind of setting, like and then actually like we would like to answer like what will be the information partition for Betty in this model. So this is a similar question to what has been asked in this week's quiz also. So maybe I should move this question to the next page. It's not too difficult. It's just a practice for how to create Aumann models. And it's, I think, not too hard. So I would like to not give away the full solution because obviously this is also as a similar question is asked in the this week's quiz also. But yeah, still we can say some things. So the agents or the players which we'll have are Anthony, Betty, and Carol. And the set of states which we'll be having is so the sigma which we'll be having is something like okay. So how many states will be there first of all? Like would anyone like to answer? Maybe before I fill up this. So how many possible states will be here? Like there are three people, Anthony, Betty, and Carol, and each can have like two acts. Each can be a two of the acts. Two, one after two colored acts. So how many? So yeah, Satvik. So Satvik is saying that there will be 2 raised to the power 3, which is 8 states. Darshan is also typing something in the chat. Okay, so Darshan is writing actually 6 states. So Darshan, I think what you did was like something like there are like so we have like 2 hats for each of the 3 people. So you did something like 2 times 3, which would come out to be 6. But actually note that the answer would be 8, like what Satvik wrote, like 2 raised to power 3. And why is this? Because Anthony has 2 choices for the hat, red or blue. Similarly, Betty has 2 choices and Carol has 2 choices. So what happens is so Anthony has 2 choices, Betty has 2 choices, and Carol has 2 choices, and all of these are independent. So we'll have 2 times 2 times 2. So 2 raised to the power 3 possible ways. And I can like sort of write down those also. So it would be 6. So how is this 6? So let's suppose one case will be all of these three have red colored hats. So like and the second case can be Anthony and Betty have red. A and B basically have red, and C has green. Oh, C has blue. Then the other case would be this would be R, this would be B, this would be R. And similarly, the next case would be this would be R, this would be B, this would be B. And now we can have the same cases, but with B's. So I hope this makes a bit of sense. Like you can count these are 4 + 4, which are 8 states. Like, and all of these states are actually distinct. RRR, RRB, RBR, RBB, BRR, BRB, BBR, and triple B. So, Darshan, is it clear? Like, why will there be 8 states and not 6? Okay, nice. So it's clear. That's nice. So, and now similarly, like, you can have information partitions for the states. So you'll have some information partitions for like, uh, you will have information partition for Anthony and Carol, which has been asked, I think, in the quiz also. So I have just asked like what will be the information partition for Betty. So we'll just be discussing the information partition for Betty. So Betty can only see the two hats of like Betty can only see the hats of Anthony and Carol, but not her own. So what do you guys think will be the information partition? Maybe just let's just add these states one by one to some partitions. Maybe like let's just do it a bit procedurally. So one of the partitions will definitely contain the state RRR, where all three are wearing R. Now, does this state RRB and RRR, can Betty distinguish between these two states? Like RRR and RRB means like basically Carol has swapped the hats. So can Betty distinguish between Carol wearing a red and Carol wearing a blue hat? So yes, Betty actually can, because Betty can see the uh, Betty can actually see Carol's hat. So Betty can actually see. So we'll have a different partition for RRB. Now suppose we see this term, the RBR term, which means that mm, Anthony and Carol are wearing red, whereas Betty is wearing B. But note that Betty can't distinguish between RBR and RRR because Betty can't see her own hat. So Betty will not be able to distinguish between these two. Similarly, if we see this omega RBB, then Betty can't distinguish between RBB and RRB because like the only difference here is Betty's own hat, and Betty can't tell about anything about her own hat. Similarly, now we see the hat, the state BRR. So BRR means that uh, Betty is wearing red, A is wearing B, and C is wearing R. Then note that this state is distinguishable from WRR, like the RRR state, because like Betty can see the colors of the Betty can basically see the colors of A and C. Similarly, it is distinguishable from these two states also, the RRB and RBB. So this will again come into a new partition. So BRR comes into a new partition. And note that similarly, BRB will also be a new partition because it can be distinguished, like Betty can distinguish BRB from all of these. So I'm just going a bit fast now because I think we have got the hang of it. And now this BBR state, note that this BBR and BRR are not distinguishable because Betty does not know her own hat's color. So B and R here Betty cannot distinguish. So BBR will come here. And now this BBB and BRB are not distinguishable because Betty can't know her own hat color. So this will be the information partition for us. So the partition will consist of basically four sets, each containing two elements. So RRR and RBR in one, RRB and RBB in one, RBRR, BBR in third, and like BRB and BBB in fourth. And I think Satvik has already written this in chat also. So good job, Satvik. So a very high level idea to think about this is a very easy way to think about this is so Betty can distinguish between like the first and the thirds, right? Like Betty, the only case where Betty fails to distinguish is when basically the second entry or basically the Betty's own hat color changes. But if Anthony or Carol's hat color changes, then Betty can distinguish. So that's why like Anthony has two choices of colors and Carol has two choices of colors. So 2 times 2 is 4. So basically, Betty can distinguish between four cases. And in each case, one case will be Betty has a red colored hat and a blue colored hat. And this is what's happening. So we have four cases in which Betty can distinguish, and each of those has like two cases in one in which Betty has a red colored hat and second in which Betty has a blue colored hat. So this is the information partition for Betty. And this will be our final answer. Maybe I'll just bold it to see for everyone to see that this is indeed the answer. Or maybe it's not bolded, just underline it instead. No, underline was bad. Yeah. So Satvik had written this answer also in the chat. So good job, Satvik. So yes, guys. So this is the answer for us. Similarly, like one can write for Anthony and Carol also, which has been asked in I think your quiz also. So yeah. So we'll just take maybe so we are now at the sixth question. Sixth question says that consider an Aumann model of incomplete information in which n is 2. So basically there are two players, there are 9 states, and we are given player 1's partition, we are given player 2's partition, and now we have to answer which of the options are correct. So I think we have discussed Aumann model a lot. So I would like you guys to note that this question can have multiple options correct. I would like you guys to think about this question and answer this. Uh, Also, like, I hope everyone knows what common knowledge is. This was also discussed in the lectures only. What is common knowledge and what is not common knowledge. Or maybe like we'll discuss this question properly. But we'll take, I think you guys can think about it for like 4 or 5 minutes. I'll come back in 4 or 5 minutes. I'll mute myself for 4 or 5 minutes and you guys can try out this question on your own and type out any answers which you come up with in chat. I'll be going to get some water in the meantime. So if you feel like you have some answer or anything, feel free to type it in chat. I'll come back in like 2 or 3 minutes and we can discuss the answer. So try this sixth question by yourself first, guys. I'll be muting myself in the meantime. Okay, so Satvik has written in the chat as answer as ABCD. So I don't know the answer myself, Satvik. I will be solving this. So I'll also be solving this on the screen so that we can see what the answer is. And so Darshan is writing, is any PDF available for this subject? You're not getting anywhere any PDF. So I think I'm not sure if anything is mentioned on the course webpage about any like course textbook, if the like is the course following any specified textbook or not. So I'm not really sure of that. But other than that, I think you guys will have access to these problem solving the. So I'm uploading all of these in form of PDFs, all these problem solving statements on the as a PDF on the NPTEL portal, like on Google Drive, and you guys might have access to the Google Drive. You guys must have been given the link to that Google Drive on which I am updating all these assigned problem solving assignments. Other than that, as a textbook resource, I don't really know of any, but I'll try to find out, and if I get anything, I'll just post about that in this chat only, in this Teams chat only. Like after the session is over, I'll try to find something, and if something I'm able to find, I'll give you guys on. I'll post on this chat the URL for that resource. But till then, I guess like if I'm also not able to find, then I guess the NPTEL lecture videos and all these problem solving sessions sheets are the ones which you can refer to in the meantime. So yeah. So till then, uh yeah. Apart from that, maybe let's just get to solving this problem now. We are given basically, we have to consider an Aumann model of incomplete information in which we are given the set of states, the players, the partitions, and now the options are all about like common knowledge. That so we are given some event and we have to tell whether this event is common knowledge in the state of the world, in different states of the world. So here we'll be using, first of all, uh, we'll be using the theorem discussed in the lectures that like whenever we have to discuss about common knowledge, this theorem comes in handy. Like an event A, an event A is common knowledge if and only if A is a like so A is basically A is a superset or equal, like superset or equality also holds, is a superset of C of W. So an event A is common knowledge in the state of the world omega. This is omega, right? This W. This is A. If and only if A is a superset of like C of W, which where C of W is nothing but the where C of W is the connected component in the graph of states described in the lectures. So there was this theorem was discussed in the lectures where suppose you take every state as a vertex of a graph and then have an edge between every pair of states which are not distinguishable like by any agent. So like if agent 1 cannot distinguish between states 8 and 9, so you put an edge between 8 and 9. Similarly, if any agent cannot distinguish between 4 and 5, then you put an edge between 4 and 5. Similarly, since agent 2 does not distinguish between 4 and 7, you put an edge between 4 and 7 and something like this. And now what we say is if we draw this graph, and on this graph, if we find a connected component and basically an event A is the maximum comments here. So an event A is the if an event A is like the superset of the connected component containing the state W, then only we can say that the event A is common knowledge. Basically, only then we can say that everyone knows that everyone knows that everyone has knows that A and stuff like that. So I hope this theorem is clear to everyone. Like this theorem has been discussed in the lectures already. So I hope everyone knows about this theorem. That so effectively for checking if something is common knowledge, uh, the go-to procedure, our go-to procedure will be like draw the graph, like consider the vertices and then draw the edges corresponding to these partition functions and just see whether for any state the event lies as the event is a superset of the connected component, superset or equal to the set of states of the connected component. So here maybe we can proceed by we can just proceed like this. We just draw the graph for this Aumann model. We are given that there are something like 9 states. So here I have drawn like something like 9 vertices here, which I have numbered. And then we have to draw edges between these, which show that the states cannot be distinguished. So we know that here according to this, the partition for the player 1, we are given that player 1 cannot distinguish between the states 2 and 3. So we draw an edge between 2 and 3. So we have an edge between 2 and 3, right? And now another thing which is given to us is player 1 cannot distinguish between 4 and 5. So we'll have to draw something like a 4 and 5 also. So draw an edge between 4 and 5 as well. And then we again have an edge between 8 and 9. So we have an edge between 8 and 9. Right. And then for player 1, we have drawn all these edges. Like these are the only edges which we need to draw for this agent, since everything else is distinguishable. Then for the second agent, we have something like second agent cannot distinguish between 2 and 5. So again, we draw an edge between 2 and 5. Similarly, draw an edge between 4 and 7 also. So I'll draw 2 edges at a time, like 2 and 5 and 4 and 7. So 2 comma 5 is an edge. Similarly, 4 comma 7 is an edge. Right? And then we have something like a 6 comma 9 as an edge. We have an edge between 6 and 9. Maybe I'll just reposition the vertices to make it a bit cleaner graph. Okay. And I think we are done with all the edges we draw. Yeah. After 6 comma 9, 8 is again like this. So this is the graph which we obtained from the Aumann model by considering like what we just described. And now we have to consider the connected components for this kind of model, for this graph. Like it's maybe easier to see the connected components. I can just maybe move this graph a bit and it will be easier for you guys to see the connected components. Like although it's not too hard, but yeah. Maybe we can move all of these side, this side. Yeah. Just put these a bit more compactly. Yeah, I'm just moving around the vertices of the graph. I'm not changing the graph. I'm just moving around the graph a little bit so that it's easier to see. So see, you can actually see that there are 3 connected components in this graph. So this is one connected component which just contains the vertex 1. Similarly, the second connected component contains 2, 3, 4, 5, and 7. And the third connected component contains 6, 8, and 9. Right? And now now basically we just have to see for any vertex, like we'll have to see the connected component and see whether the event is a superset of that connected component or not. Let's move on to the problems then. So we have to answer. Let's do it option by option. So option A says that the event 23457 is common knowledge in the state of the world omega equals 5. If omega equals 5, then what's the connected component for this? The connected component consists of basically the maximum connected component consists of this. It has the states 2, 3, 4, 5, and 7. So it contains all of these states, the 2, 3, 4, 5, and 7. So any event should be a superset of 2, 3, 4, 5, and 7 for it to be a column common knowledge in the state 5. And note that this event is actually exactly that. The 2, 3, 4, 5, 7 is exactly the connected like the event. And this is also the connected component. So this is common knowledge actually. So we know that C of 5 is equals to 2, 3, 4, 5, and 7. Hence, the event A equals, maybe I should just put here A also. Hence, the event A equals 2, 3, 4, 5, 7 is common knowledge. Or maybe we can just write it can be seen from the graph that maybe I'm just trying to be a bit more verbose so that it's a bit clear to everyone. And C of 5 equals A. So A is common knowledge in the state 5, right? Now let's move on to option B. Option B says the event 689 is common knowledge in the state of the world 9. Let's see in the graph what's the connected component of 9. So it is precisely 6, 8, and 9. So for 9, the connected component is 6, 8, and 9. And this is the event which has been given to us also. So again, like we need the event to be a superset, like event can be a superset or equal. Like here it is exactly equal. Even if it was a superset, then also we would have been fine. But inequality also we are fine. So again, we can see that maybe I'll just copy and paste this kind of thing and just change the values. So it can be seen that the connected component of 9 just consists of the state 6, 8, and 9, right? And we are given that and we are given that the event A is also 6, 8, and 9. So C of 9 equals to A. So this is common knowledge in state 9. So B is also correct. Now let's move on to option C. Option C says that the event 2, 3, 4, 5, 6, 7, 8, 9 is common knowledge in the state of the world 2. So let's just see again the connected component for 2. So for 2 also the connected component is something like this, which was previously the connected component for 5 also. 2, 3, 4, 5, and 7. So we have that. Like I'll just copy this because the connected component is the same. The connecting component for 2 is also like 2, 3, 4, 5, and 7. And note that the event which we are given, the event A which we are given, has something like 2, 3, 4, 5, 6, 7, 8, 9. So we are given and you can see like 2, 3, 4, 5, 7. All of these entries are contained in the event A, like 2, 3, 4, 5, and 7. So actually this event A is a superset of C of 2. Hence, A is a superset of C of 2, and hence and so on is common knowledge in state 2. Right? Now let's move on to option D. Option D says that the event 1 is a common knowledge in the state of the world omega equals 1. So in the state 1, in the omega equals 1, let's see the connected component for 1. So yeah, so in the maximum connected component of 1, there is just 1 and nothing else. And note that the event is also just containing 1, so event and the connected component are equal. So again, it will be common knowledge. So maybe I'll just copy this template again and paste this. It can be seen that C of 1 is 1, and so A is common knowledge. So we have that A, B, C, D, all options are correct. So none of these will definitely be not correct. So hence options A, B, C, D are correct. Yeah, I hope this makes sense. This is what Satvik also wrote in chat. So good job, Satvik. Again, if Darshan or Satvik, you have any doubts along the way, you can ask me. Feel free to ask me, in fact. Okay. Now we have the seventh question. So seventh question is a bit challenging. Maybe I'll first discuss the eighth question because eighth question is more similar to what would be asked in the quizzes. What is asked in the quiz? Eighth question says that consider an Aumann model of incomplete information in which n equals to 1 comma 2. So there are like two players or two agents, and the set of states is 1, 2, 3, 4 till 8. So we have 8 states and the partitions which are given to us, and there are these partitions also given to us for the two players. And let A is the event 1, 3, 4, 5, and B is like 1, 2, 3, 4, 5, 6, 7. Then which of the following statements is are correct? This is, I think this question is something which is more relevant as this makes us more familiar with knowledge operators and everything. So I think we should discuss this next question first. Uh, Maybe we can go option by option here. So option A says like K1 of A should be 1 comma 2. We know that the set A is 1, 3, 4, 5. And if we take K1 of A, we have to consider the partition for the agent 1. And for the agent 1, what do you guys think K1 of A should be equal to? If we have to consider the state 1, then 2 should also be present in A. But note that 2 is not present in A. So 1 will also not be present in A. Similarly, if we have to include 3 in K1 of A, then 3 and 8 are indistinguishable. So 8 should also be present in A. But note that 8 is not present here. So 8 will not be present, like 3 will also not be present in K1 of A. Now, if we have to talk about 4, if 4 is present in K1 of A, then 4 is indistinguishable with 6. This means that 6 should also be present in A, but it is not. So 4 will also not be present in K1 of A. Similarly, if we talk about 5, 5 is for 5 to be present in A, like 7 has to be, for 5 to be present in K1 of A, 7 has to be present in A, but it is not. So 5 will also not be present in K1 of A. So can you guys see that K1 of A will actually be empty? I'll denote empty set as something like this 5. Right? Because none of these 1, 3, 4, 5 uh, have their corresponding next entries inside the set A for K1. Right? And now since we have like K1 of A is 5, like we don't, so then we'll have something like this will reduce to like something like K2. So what this notation means is that we are taking K2 operator over K1 operator over A. We know that K1 of A we have just described that it is equal to 5. So then this whole thing reduces to 5. Then what will be the value of K2 of 5? What is like a K2 of an empty set? Can any of you answer in the chat? Yes, so as Satvik said, so K2 of 5 will be empty set. Note that knowledge operator over an empty set will be an empty set, right? So yeah, maybe I should just copy this 5. Since K1 of A is 5, hence K2 of K1 of A is equals to K2 of 5. Yeah. And which will again be equal to 5. So yeah. So K2 of K1 of A is actually 5. And what will be option C? Option C is K1 of K2 of K1 of B. So guys, can you try this out yourself? Like I would like you guys to try like C and D options yourself. What does K1 of K2 of K1 of B come out to be? What does this say? Okay, so Satvik is saying that K1 of K2 of K1 of B should be 4, 5, 6, 7. Let's see what this should be. So K1 of B, let's first of all see what K1 of B comes out to. Come. Okay, so we are given this set B as 1, 2, 3, 4, 5, 6, 7. And now we are taking K1 operator over this, right? For 1 to be present in K1 of B, like 1 is indistinguishable with 2 for 1 and for the player 1. And note that 1 and 2 both are present in B. That's why these 1 and 2 at least will be present in K1 of B. Or maybe like a faster way to check would be like just check if this partition, a whole partition, this 1 comma 2 is present in B or not. So here you can see that 1 comma 2 are present. That's why these will be part of K1 of B also. Then check for the next partition, the partition 3 comma 8. If these two elements together are present in the set B, note that 3 is present but 8 is not present. So this partition won't be part of K1 of B. Like this set will not be a subset of K1 of B. Similarly, check for this set 4 comma 6 if it is a subset of B, and we see that 4 and 6 both are present. So indeed this is. So this will also be part of K1 of B. So this will be 4 comma 6. And then for the next set 5 comma 7, we again see if 5 and 7 are part of B, which you can see they are indeed. So 5 and 7 are there. So 5 and 7 will also be. And yeah, so this will be the K1 of B. And yeah, so this is 1, 2, 4, 6, 5, 7. And this is what Satvik also wrote. So good job, Satvik. So K1 of B is this. And then we have to find out like K2 of K1 of B. So K2 of K1 of B, like I'm trying to calculate this step by step. I'll first calculate K1 of B, then I'll calculate K2 of that, and then I'll calculate K1 of that. K2 of K1 of B will be something like K2 of this set, right? And what will this be equal to? Should put this in next line. So we have to do K2 of this set 1, 2, 4, 6, 5, 7. And K2 of this set, now again, since we are taking K2, we have to consider the second partition. Just consider the for the second partition, like F2. Let's consider the first set 1, 2, 8. Are all of these entries a subset of this set? So 1 and 2 are present, 8 is not present. So this won't be a part of uh, K2 of like this set. Then we have the partition as 3. Is 3 part of the set? No. So again, we don't have this in our set. And similarly, let's check for the 4, 5. Are 4 and 5 subsets of this set? So 4 is present, 5 is present. So yeah, it is indeed a subset. So 4 and 5 will be present. And similarly, let's check for 6 and 7. If 6 and 7 both are present in this set. So 6 is present, 7 is present. So 6 and 7 will be a part of this. So K2 of K1 of B comes out to be 4, 5, 6, 7. And now, like, if we have to take K1 of K2 of B, what does this? Yeah. This is just equal to, so K2 of K1 of B, we just calculated it as 4, 5, 6, 7. Now we have to take the K1 over it. So K1 over this set 4, 5, 6, 7. And this will be equal to, again, we are taking K1 operator. So just check again for all the sets of the partition, whether they are a subset of this 4, 5, 6, 7 set. So note that we first check for these 1 and 2 set. Note that 1 and 2 are not present in this 4, 5, 6, 7. So this won't be present in the K1 of this. And similarly, let's check for 3 and 8. So 3 and 8 are also not present. So they also won't be a part. Now 4 and 6, note that 4 and 6 are present here. So 4 and 6 will be a part of this thing. And let's check for 5 and 7. So 5 and 7 are also present. So they will also be a part here. So K1 of K2 of K1 of B will come out to be, like we could have written it as 4, 6, 5, 7 or 4, 5, 6, 7. It does not matter. So K1 of K2 of K1 of B will come out to be 4, 5, 6, 7. And this is what Satvik wrote, also like the final answer as 4, 5, 6, 7. So good job, Satvik. Yeah. And note that this is not equal to 1, 2, 3, 8. So this option will be incorrect. Now let's do the option D. I should just leave some spaces between options. Yeah. In option D, we have something like K2 of B. So what we have is K2 of B. And what will be K2 of B? Let's just see here. So B is 1, 2, 3, 4, 5, 6, 7. And we have to consider these partitions now since we are taking K2. So are 1, 2, and 8 part of B? So 1 and 2 are there, but 8 is not there. So this set won't be a part of K2 of B. So let's see if 3 is present in B. So 3 is indeed present. So 3 will be a part of K2 of B. Now let's see if 4, 5 both are present in B. So 4 is present, 5 is present. So these will be also part. This will be 4, 5. And then let's check for 6 and 7 are both of these present. So note that 6 is present, 7 is present. So yeah, so 6 and 7 will also be a part. So we have that K2 of B is 3, 4, 5, 6, 7. And now we have to take something like K1 of this thing. So K1 of K2 of B is equals to, like, we have to find K1 of K2 of B, and K2 of B has been reduced to this set. So we'll be having something like this, and K1 of this set. If we have to take K1 of this set, we'll again consider F1 since we are talking about K1, and we'll have So first check the set of 1 comma 2 are 1 comma 2 present in this set. They are not. Similarly, are 3 comma 8 present in the highlighted set. 3 is present, 8 is not present. So this also won't be there. Is 4 are 4 and 6 present in the highlighted set. 4 is present, 6 is present. So 4 and 6 will be there. Are 5 and 7 present? So 5 in the highlighted in this set. So 5 is present, 7 is present. So they both will also be part of this. So we have K1 of K2 of B as 4, 6, 5, 7. And now we have to find out like something like K2 of K1 of. So like this might seem a bit boring, but this question has been made just specifically for like practicing, like to figure out how the knowledge operator works. Yeah, this may seem tedious, but let's just do this. So we are more comfortable with the knowledge operator, right? Now we have something like a K2 of K1 of K2 of B will be just like taking K2 of 4, 6, 5, 7. And what will this be equal to? So if we are taking K2, we'll be considering this set. So let's just take 1 to 8. Are 1 to 8 a subset? No. Is 3 present here? It is also not present. Are 4 and 5 present in this? They are. So we will have 4 and 5 here. And are 6 and 7 present here? So they are present indeed, 6 and 7. So they will also be a part of K2 of K1 of K2 of P. And now we have to take like K1 of all of this. So this becomes something like K1 of 4, 5, 6, 7. So, and this, one second, guys. So, and now we have to take like K1 of 4, 5, 6, 7. And what will this be equal to? So if we have to take K1, we just have to consider these sets and note that 1 and 2 are not present in 4, 5, 6, 7. Similarly, 3 and 8 are not present in 4, 5, 6, 7. Similarly, is 4 and 6 present? So 4 and 6 is present. 4 and 6 will be a part. 4 and 6 will be a part. And then 5 and 7 are also present. So 5 and 7 will also be present. So note that K1 of K2 of K1 of K2 of B will be actually equal to 4, 6, 5, 7 or 4, 5, 6, 7, which is obviously not 1, 2, 3, 6. And yeah, so Satvik also wrote the answer as 4, 5, 6, 7. So again, good job, Satvik. I guess you are now very comfortable with the knowledge operator. So let's see what all options are correct. So C and D are definitely incorrect. B is correct and A is incorrect. Only option B is correct. And only option B is correct. Okay, so we should just ignore this. Yeah, I had one more question which I thought maybe I'll discuss, but I think we are out of time, so I'll just remove this question. Yeah. So we discussed overall 7 questions today. Okay, then. Uh, I guess we have discussed all the questions. Yeah, I think I guess we are done for the day from my side. If any of you has, since we are almost out of time also, so Satvik or Darshan, if you guys have any doubts, maybe you can ask in like 2, 3 minutes, and if not, like maybe we can also close the session. Satvik or Darshan, do you guys have any doubts? Okay, I guess since none of you is responding, I I see this as a sign that there are no doubts, and that is a good thing, or maybe a bad thing. I don't know, but yeah. Okay then. So guys, thanks a lot for joining for today's session, and I hope I'll see you guys next week. Also, same timing, Monday 6 to 8 p.m. Uh, till then, like I'll be closing the session and I'll be uploading the recording on YouTube also. Okay then. So see you guys next week. Bye bye, guys. You can leave the session.